All right, let's turn our attention to structures. Here's a structure. That's the Sagrada Familia Cathedral in Spain. We aren't going to be able to do quite as elaborate a thing since we're just using C. Here's a really big structure. So the point of C structures as compared to C arrays is that they're heterogeneous. We can store multiple different types of things inside of a C structure, whereas arrays have to have the same type. And then here's the structure that we're going to use for this example. It shows again, just as a reminder, the declaration syntax in C. You tell it struct, and then you give the struct a name typically, although you can also just declare it without the name, but we'll call ours rec. And this structure is going to contain an integer array with 4 integers in it, a size t, which is going to be called I, and then we're going to have a pointer called next, and this looks kind of weirdly circular, right? Because we have struct rec defined out here, and then in its own definition, we're using its declaration, which it turns out is legitimate in C. It sort of suspends disbelief when you try to refer to the structure that is the thing that you're defining it inside of. So this is entirely fine. We basically are going to be able to use this to create, say, a linked list of these structure records. And this is a pointer. So we have an integer, a size t, and a pointer to a struct rec inside of our structure. All right, so how is this represented in memory? Well, this is an illustration of that. You can see that in this section we have our integer array, and we're showing the 4 elements of that array. And we know that those are 4 bytes wide. So that's a 16 bytes, and we can see that if the beginning address of this structure is at 0, then the end of that is or the beginning of the next piece is going to start at 16. The size t is going to be an 8-byte value. It's going to turn out to be an unsigned long, I think. And then, so that takes us up to offset 24, and then the pointer, the struct rec pointer, is also 8 bytes because we're on a 64-bit architecture. Some things to note about this structure and how it's represented in memory. First of all, each of these structures is going to occupy a specific block of memory, and it's going to be a large enough block that it can hold all of the fields in the structure. So this C compiler isn't going to split these apart. It's not going to store each of the elements of the structure into different parts of memory or something like that. It's just going to allocate a single block. Notice also that the fields in the structure up here are ordered in the same sequence as the fields in the structure itself. So the integer array comes first, and the size of t, then the structure pointer comes last. And there isn't any attempt to try to compact the elements, and we'll talk more about this in a minute, but in this particular case it turns out the elements all kind of snug up next to each other in memory just fine, but that's not necessarily the case, and the compiler won't try to force that. The compiler's job is to take this declaration that we create and figure out what's the overall size of that going to be in memory, and then how do the various fields end up getting allocated in memory. It's important to note finally that machine level representation of this structure has no notion of a structure or anything like that. All that's going to happen is we're going to see memory accesses to different parts of the structure itself, and the compiler is going to orchestrate all of that. The machine itself, the processor, the CPU, doesn't have any notion of structures any more than it has any notion of arrays or anything like that. So having defined a structure, let's talk about how we access its elements. You're familiar already probably with the dot operator, and if we have a structure that's declared as such as opposed to a pointer to a structure, we can just use the dot to reference its elements. So to get to the array A, we just say record dot A and then give an index to figure out which of the integers in there we want to talk to. If we want to get at element I, we just say record.I and then record.next to get to the pointer. That's all fine and good, but it's quite common in C to pass around pointers to structures, as shown here in the next example. So here we've got a structure record pointer called R, and we're initializing it to have the address of some existing record of that same type. Now, in order to access a value through a pointer, we would normally say something like star R, and then give the element within the structure that we want to refer to. So star r.I. Here's the problem with that. It turns out that the dot binds more tightly than the star. So if we were to write this out in full with parentheses, the way that the compiler interprets that is the thing pointed to by r dot I. Well, whatever is stored in I is probably not a pointer. In fact, it's going to be something that's of type size of t, so that's going to just be completely bogus on the face of it. Instead, what we really want to do is have it bind the opposite direction. We'd really like to be able to say we want to have star r, dereference that pointer r, and once we've dereferenced it, then grab the I element out of that structure. So that's really what we want when we're trying to access an element within a record or a structure that's pointed to by variable r. Now, that happens often enough that C actually provides us some syntactic sugaring for that parenthesis star r paren dot I, and that's what I'm showing up here. So the arrow operator, r arrow I, is syntactic sugar for exactly that construct. So when we're trying to refer to, say, the 0th element of array A at a structure pointed to by r, we use the arrow operator. And similarly, to refer to the I element of the structure pointed to by r, we use the arrow operator as well. The rule of thumb here is that if you actually have an instance of the structure, you almost always are going to use the dot. But if you have a pointer to the structure, you're almost always going to use the arrow. And that's going to take care of 95% of all the cases you're going to encounter in the wild. So now that we know how to access the various values inside the structure from C, let's take a look at how this gets converted into assembly language. So we're going to start out with the same structure as before, and we're going to take a look at how we implement this function getAP. What it's going to do is grab a value that points to a struct rec, that's the star r here, and then an index, and it's going to grab the value from the A element of the record at that index and return not the value but the address of the value. So we're giving back the ampersand of that expression. And you can see down here at the bottom kind of what we're after. So we've got our pointer r that's referring to one of these structures, and we know that the first portion of the structure is an integer array of 4 integers. So because each of those integers is 4 bytes, there's 4 bytes, there's 4 bytes. And we want to fish out the value that's at the index given by the second parameter of that function. We want to basically take that index, multiply it by 4, and then add that to the beginning of the structure. The assembly code to do that is really quite simple. It's just this one instruction basically. RDI is going to be our first parameter to the function, so that's going to actually be the pointer r. RSI is going to be the second argument to the function, so that's going to be the index value. And we know that the scale factor is going to correspond to the size of an int of 4 bytes. So we're going to take RDI plus RSI times 4, which is exactly this expression here. And then we're going to do a load effective address, the point being that we're trying to return the address of that thing, not the actual value that's being stored there. So the load effective address calculates the address and stores it in the destination register RAX, which of course is going to contain the value of the function return. So we've done the address calculation, and that's all we need to do here. We're not doing a move instruction here. We're just getting the address, doing the calculation, and storing the result in the return register, and that's what the caller is going to expect. As I mentioned previously, one of the reasons that the syntax of C allows us to declare pointers to ourselves essentially inside of a structure is it makes it straightforward for us to implement structures like linked lists or trees or other things that involve pointers. So let's take a look at how we would use this structure as a linked list of these records. So the illustration here shows 3 of these where I've got 3 instances of this structure, and I have access to this first pointer that refers to the first thing in the list. And then for each of the elements in the list, the third section of the structure, this next pointer itself, contains the address of the beginning of the next structure in the list. And that one's next pointer contains the address of the beginning of the third one in the list. And finally, at that point in this illustration, at least, we've got an indication here with a slash that this is the null pointer. So the value of that next pointer in this third one is just 0. Okay. Let's take a look then at a function that's going to traverse this linked list structure. So we're going to get as our parameters to this set bar function two things: a pointer to the beginning of the list, which is just a pointer to one of these struct rects, and then a value bar. What it's going to do in the business end of the loop here is it's going to grab the value of I out of the current structure that we're pointing to and store that in this local variable I. And notice, because we've got a pointer to a structure, we're using the arrow notation to fish the value out. So that gives us the value I, and then what we're going to do is we're going to take the A array, and at its ith element, we're going to set that value to bar, this value that we passed into the function. Again, because we're referring to this thing through a pointer to the record, to the structure, we're going to use the arrow notation. Now notice that the main control structure here is a while loop, and we start out with while r, assuming that the first value passed in here was a pointer to a existing structure of this type, like we've shown in the illustration up here. This is going to be a non-zero value, and again, C just treats 0 as false and anything else as true. So even though it's a little weird to think about a pointer as having a true or false value, that's what's going on here. We're saying that as long as it's true that this pointer points to something, in other words, it has a value other than 0, we're going to keep looping through. So the first time through, that thing is going to point to the first instance of this structure, update the appropriate element of the A array to include bar, and then it's going to hit the final statement here that's going to update R to point to the next structure in the list. So the first time through, it's going to grab this value of next, stick it in R, and that's because that thing actually points to something that's not 0. There's a legitimate element of this structure at that location. We're going to take the loop again and update the contents of the appropriate value in the A register with bar, and then do the same thing. Grab the next pointer out of that structure, and then do the same thing again with this third element in the list. By the time we get to this statement, though, in the third element, the value for next at that point is the null pointer. It's a 0. So we'll loop back to the while statement. This will now be a 0 value, and we'll want to bail out of the while at that point because we've now traversed the entire list. Let's take a look at the assembly language for this. If we go back to this original declaration of the structure, we know that because this is an integer array that contains 4 integers, and each of those integers is 4 bytes wide, the total size of this array is going to be 16 bytes. Notice here in the code, in the source code, what we want to do is fish out the value of the I value in that structure. So we know in order to get to that I value, we've got to skip forward 16 bytes from the beginning of the structure to that location, and that's the value we want to get and use for I. So the first thing that's happening here in the assembly language is that we've got a move instruction that goes 16 bytes beyond the value of RDI. And as we're familiar with already, the first parameter to the function is going to be stored in RDI, the second parameter in RSI. So what this is doing is beginning at the beginning of the structure that it's working on currently, which is in RDI, add 16, just a fixed offset, and then grab the value there and store it in RAX. We're not using RAX as a return value so much here because this function is declared to return nothing. It's a void function. So we might as well use RAX as not, and that's what the compiler chooses to do. So we're basically putting the value of I, this local variable, in RAX. Now what we want to do is put, in the next statement, we're trying to take bar and assign it to the ith element of that array A. Well, we know that bar is coming in as the second parameter, and that will be stored in RSI. So then the second statement, the SI register is being used as the source of a move. So that's going to be that's going to be the bar value. And where it's going to get stored is at RDI plus RAX times 4. We know that RAX is going to be the index into the A array, right? That's what we calculated in this first statement. I, stored in RAX, is the location in the A array where we want to store that value bar. So by taking RDI, which is R, plus the index or the value of I times 4, that gives us the appropriate location where we want to store the value that got passed in as bar. And this move instruction accomplishes that. So that takes care of this instruction, and finally we want to deal with the assignment of the next pointer to the control variable of the while loop. Again, we know from the structure that's laid out here in memory that we've got 16 bytes for the array of integers. We're going to have another 8 bytes for the size t parameter, which gives us a total of 24 bytes, at which point this next pointer appears in the structure in memory. So just like we did in the first instruction where we offset 16 bytes from the beginning of the structure, now we're going to offset 24 bytes from the beginning of the structure, grab that value, and put it actually back in RDI, because that's where we're storing the loop control variable, which we also happen to have passed in as a parameter to this function. So that updates RDI. Now we've got to check to see if we're at the end of the linked list. That's going to be true if the value of R is 0, so we run a test instruction, which does the equivalent of a logical AND between RDI and RDI, purely for the purpose of deciding what the condition codes should be. So in particular, and we can tell this by looking at the jump not equal instruction at the end here, we're trying to check to see if RDI is 0. We'll set the flags, the condition code flags, based on this test queue operation. If it's not 0, that means that we're not at the end of our linked list yet. So the jump not equal back up here to to L11 is the iterator. On the other hand, when we get to the end of that linked list, and then this pointer is null or 0, the value or the flags that will be set based on the test queue operation will indicate to the jump not equal that it is equal to 0, and it will fall through to the next instruction, which presumably is going to be a return statement that goes back to the caller. All right, let's talk about how the compiler is going to allocate structures in memory. And for this example, we're going to use a different structure. So this new one's defined up here. It's called structure S1, and it contains 3 elements: a char that's called C, followed by an integer array that has 2 integers in it, that's called I, and then a double called V. What we might expect based on this declaration, when we think about how the compiler might put that in memory, we know that a char is 1 byte, that an integer is 4, so 2 4-byte values is going to be 8, and a double is going to be 8 bytes. So we might expect the compiler to allocate space in memory like this, where if P is the beginning of the memory that this thing is going to be stored in, we might have 1 byte for C, and then at P plus 1 we'd store the first of those integer array elements, and then at P plus 5 the second of those, and at P plus 9 the value for V, that double, and then the beginning of the next chunk of memory would start at P plus 17. It turns out that although that seems like a very memory efficient way to do this, that the compiler will not store the structure in that form. And this relates back to something we've talked about previously in the course, where the compiler is going to only allocate storage for values at a multiple of the address corresponding to their size. So if it's trying to store integers that are 4 bytes wide, it's going to store those integers always on a 4-byte boundary, or in other words, an address that's evenly divisible by 4. Or if it's trying to store a pointer or a double or a long, which are 8 bytes wide, it's going to always store those at an address that's a multiple of 8, or an address that's evenly divisible by 8. So in fact, the way that would store this information, or store this structure in memory, is shown in the second example, where P again is the beginning of where this gets stored, and we're going to put the character at the very beginning of that. Because the character is only 1 byte wide, we can store it at any location in memory, because any location in memory is evenly divisible by 1. But now when it comes time to allocate space for an integer, so there's these 2 integers here that correspond to that array I, that's got to be stored on a 4-byte boundary because integers are 4 bytes wide. So we're going to skip forward to the beginning of the next 4-byte boundary and store those integers at P plus 4 and P plus 8 instead of P plus 1 and P plus 5, as would have been the case if we were not worried about aligning data. that means that we're totally losing 3 bytes of storage every time we stamp out one of these structures. That's kind of the price that we pay in terms of storage compaction in order to be able to make it easier for the processor to access these values. So that brings us up to, we've got p plus 4, p plus 8. So this thing ends at p plus 12. But p plus 12 is not a multiple of 8, right? And we want to try to store a double value, which is itself 8 bytes wide. So again, we're going to skip some space. We're going to skip these intermediate 4 bytes to get ourselves up to an address that's an even multiple of 8. And that's where the value v is going to get stored. Here's some kind of common principles for how we need to worry about alignment of values in memory. So aligned data. Basically, what you can think of this, the way you can think of this is to just say, well, each of the primitive data types has a requirement for k bytes of data. And the notion of alignment that we just talked about says that that address has to be a multiple of k. The reasoning behind this is that the processor is actually going to access memory in 4 or 8 byte chunks. And we'll talk about this more when we start talking about caching. And it turns out that it's really inefficient for the processor to have to access memory at locations that cross these kind of quad word boundaries. And in particular, it makes the virtual memory system a lot harder to implement. So when we're talking about caching, virtual memory, other sorts of things, we're trying to play nice with those mechanisms that we haven't really talked about yet. But that's really the underlying reason for the compiler wanting to locate things in memory in such a way that's going to make it easy on the virtual memory system. So the compiler, aware of the kinds of architecture that it's generating code for, is going to insert those gaps to keep the fields aligned on these boundaries. We've got different fundamental values of different sizes. Chars are characters that are 1 byte, shorts that are 2 bytes, ints and floats are 4, doubles, longs, and pointers are going to be 8 bytes long. One way to think about this in terms of the addresses that they're going to be stored at, when we talk about a multiple of 4 or multiple of 8, it doesn't really map so well into the decimal number system, but in binary, if you think about the addresses in binary, there's no constraint really on characters because they can be stored at any 1 byte boundary. But when we're talking about a 2 byte boundary, you could think of that in the following way, that you're saying that the least significant bit of the address in base 2 is going to be 0. And then to get a 4 byte boundary, you would ensure that the least 2 significant bits are 0. And to get an 8 byte boundary, the least 3 significant bits are going to have to be 0. So here's 2 to the 3rd, 2 to the 2nd, 2 to the 1st, 2 to the 0th, right? That talk about the multiple of the address that's valid to store each of these different sized data types. The constraints we've been talking about so far, although we're doing it in the context of structures, are really not specific to structures. Anytime we store an integer or a float or a pointer in any place in the program, we're going to store it according to the boundaries implied by the size of that fundamental data type. An additional complication that arises when we're dealing with structures is, where do you put the structure itself in memory? We know that the individual elements have to be aligned on the appropriate boundaries, but what about the structure itself? The algorithm the compiler will use is it's going to look at all of the elements within the structure and find the largest one, and then figure out the size of that largest element. So in the previous example, we had a double called v that had 8 bytes. So in that case, k would be 8. It would be the largest element, and we know that those elements of size 8 have to be aligned on 8 byte boundaries. So what the compiler will do then, in order to make the addressing work out properly, is 2 things. First of all, it will make sure that the initial address where that structure lives, so the very first byte of that structure, is a multiple of that value k. And that's true even if the largest thing in the structure doesn't appear at the beginning of the structure. At some point, that largest thing is going to appear in one of the elements of the structure, and it's going to have to fall on some 8 byte boundary in this case. So even if it's not the first thing in the structure itself is all going to be aligned on a multiple of its size. And then the structure itself, the overall size of the structure, is also going to be a multiple of that value k. These 2 things taken together make it easier for the compiler to, for example, allocate arrays of structures. So if we have multiple instances of the same structure stamped out sequentially in memory, the alignment restrictions are going to work out properly. Then, as we've already seen, within the structure, the compiler is going to satisfy each individual element's alignment constraints. So here's an example of alignment within a structure. We've already kind of worked through this, right? We know that the largest thing in this structure is a double, this guy. So the value for k is going to be 8, and we need to make sure that we satisfy each of the elements' alignments. And we've worked through this already on a previous slide. That's why we had this 3-byte gap and this 4-byte gap that we looked at previously. We also want to think about the overall structure itself. So here's a slightly different version of a structure that contains these same elements. I've got a new structure here called S2, and we've now rejiggered the ordering here so that the double is coming first in memory, followed by the integer array, followed by the character. And what you get here again, the initial address has to be a multiple of k. The largest element is going to be a double. So p is going to have to be a multiple of k when the compiler allocates it and when the linker puts it into memory. Then the structure itself has also got to be a multiple of k. And we can see here that the resulting structure has k plus k plus k, right? So it's 24 bytes wide, which is a multiple of that largest structure's size. In this particular case, it's able to compact the memory a little bit better because the compiler is going to observe the ordering of the elements in the structure itself. It's going to put v first in memory, occupying 8 bytes, then 4 more bytes for each of the elements of that array for a total of 8, and then 1 byte for the character. And because it's got to observe this alignment and restriction for the overall structure, it's still going to have to pad this guy out by 7 bytes to get up to a multiple of 8 bytes for the whole structure. We didn't really save any extra space by rearranging the structure in this fashion, but it's definitely true that in some cases you will have less wasted space by choosing an appropriate ordering for the structure itself. We can also have arrays of structures. So in this case, we've got that same structure S2 that we've been looking at before, but now we're defining an array of 10 of those things called A. So here's the beginning of array A. We've got one of those structures, which we know from the previous page is 24 bytes wide. So at A plus 24, we're going to start the second element of it at A plus 48, the third element, and so forth going forward. Let's see how we would access the contents of a structure inside of an array. So we're going to use a new structure for this example. It's called S3. It's going to have these 3 elements, a short called I, that's 2 bytes, a float called V, which is 4 bytes, and another short called J, which is also going to be 2 bytes. And this is going to be an array of 10 of those structures. So if we look down here at the way this is going to be allocated in memory, we can see that we've got our first short value I at the beginning of each of these structures. Then because the next element in the structure is a 4-byte aligned float, we're going to skip over these 2 extra bytes so that this guy starts on a 4-byte boundary. And then right after that value v, we can store j directly in memory because it is only got to have a 2-byte alignment. But we also know that the overall size of this structure is going to be determined by the size of its largest element. So this is the value that we were talking about as capital K before. And that says that the overall size of the structure in memory has to be a multiple of k. So we already allocated those bytes, and we've allocated only the short here, j, but that's not a multiple of k. We got to add these extra 2 bytes to pad that out to be a multiple of k bytes overall. All right, let's think about how we would access elements of this structure when it's stored in an array of those structures. So like with accessing elements in a 2-dimensional array, we recall that we first of all found the beginning of a row, and then within that row we found the beginning of the column and then got the value out of that location. We're going to take a similar kind of 2-step process here, where we're first of all going to start by finding the location in the array where the structure of interest is stored. So that's step 1. And we know that because each of the elements of the array, the structure S3, have 12 bytes, what we really want to do is take whatever index we're trying to get to and multiply it times 12. It's that simple. So this is, actually this is wrong, I shouldn't say alignment space. The 12 is the size of the S3 structure, and we're going to multiply that times IDX. Okay? Once we've gotten to that location, so if IDX is, in this case, 2, we're going to skip forward 1, 2, structure's worth of memory to arrive at the structure that we're trying to access. And that's going to be at 12 times IDX, plus the base address of the whole array, of course, which is going to be located somewhere in memory by the compiler and the linker. But once we've gotten to that first address, now we want to be able to advance to the location of J itself, because that's what we're trying to fish out here in step 2. We know that that's at offset 8 within the structure, so all that has to happen is that we're going to advance from wherever we ended up here in the first step, 8 more bytes, and that's going to have the location of J, which we can then retrieve out of memory. So let's see what that might look like in assembly language. Here's a very simple function called getJ that just takes the index value, and it's going to go into array A at that index location, and then using the dot operator fetch out the value of J. Again, because we have the actual structure here, we use the dot instead of the arrow. Again, remember that the first parameter of a function gets passed in as RDI, and that's what we're going to use here in the assembly code. So we know that because this structure is 12 bytes wide, we want to be able to start at the location of the beginning of the array and advance 12 times whatever the index value is. Rather than compile in a 12 and use the multiply hardware in the processor, the compiler is smarter than that. It decides to compile into assembly code that's going to calculate 3 times 4 times the index, and then use that as the base address for the structure of interest. So we're going to take in the first instruction here RDI plus RDI times 2, which is going to give us RDI times 3, or 3 times the index value that we passed in here in the source code, and it's going to store that in RAX. It then needs to multiply that times 4 to get an offset of 12. So because there's a missing argument here, that's going to be a 0 plus RAX times 4. So that's going to effectively give us 12 times the index. And then in addition to that, we're going to add to it the location of the base of the array, right? That's this guy right here, plus 8 bytes, which is the offset within the structure that we need to advance into memory to get at J. And because the compiler knows about the size of that underlying structure, it can generate that 8. The A here is actually going to be resolved at link time to point to the actual location of this array in memory, wherever that happens to be. But at the end of the day, we're going to basically start at A. That's what the A here is going to do. We're going to advance forward by 12 times the index, which might take us to here if the index was 2. And then we're going to add 8, which is going to advance within this to get us to where J is located in that instance of the structure. As I mentioned before, you can often improve the memory utilization of an array of structures, or even just an individual structure, by rearranging the sequence of the elements within the structure. So here's an example of structure S4. It's got a char, an int, and another char. And if we order things in this way, here's how the memory is going to get laid out by the compiler. It's going to maintain the ordering of the declaration. So the first thing that's going to be allocated is C, but because the next thing that wants to be allocated is an integer, although the C can be on any boundary, the integer has to be on a 4-byte boundary. So if we assume that the beginning of this allocation is a 4-byte boundary, for example, we're going to have to throw away 3 bytes in order to get to the next 4-byte boundary in memory where we'll store the integer, and then we'll store the second character D, but because we have to have the overall alignment, or the overall size of this, be a multiple of the largest thing in the structure, we've also got to add on 3 additional bytes here at the end to get this up to a total of 4 plus 4 plus 4, or 12 bytes. We can rearrange these in a different order. So now we'll place the integer first, followed by the 2 characters. We can allocate the integer immediately at the beginning of the space because we're assuming a 4-byte boundary up here. That takes up 4 bytes. And then the C and the D values, because they're only 1 byte, can be allocated on any boundary that we want. And then we still have to obey the overall alignment restriction that says that the amount of memory allocated for the structure has to be a multiple of the size of the largest element in the structure, which is 4. So we have to pad this out to be 8 bytes wide. So we've got the same information being stored here in I and C and D, but because we've reorganized the layout of the structure itself in our source code, we're basically saving 4 bytes every time we stamp out one of these structures. And if we had just one, it wouldn't really be such a big deal, but if we had an array of 1,000,000 of these structures, we would save quite a lot of space when we reorganize the structure itself. This is a great example of where knowing the underlying structure of the assembly language that's going to be generated by your source code can help you a lot. If you didn't know how the structure was going to be allocated in memory, you might think that it really doesn't make any difference how you order those elements. But with the knowledge that they're going to have to be aligned on particular byte boundaries and that the compiler might open up extra space, you can save considerable amounts of memory.